Alrighty, good morning everybody. Welcome back to Non-Euclidean Geometry. Plan for today, so I have a quiz for you as promised, and then we're going to finish our section on the Betweenness axiom. We're going to finish our proof that we started last time, and then continue on with, look at one more theorem today. And if we have time, we can start in on Wednesday stuff. Just give you a sneak peek for the rest of this week. Wednesday, I'm planning on spending the day being our how do we compare sizes of infinite set, different sizes of infinity day. And then Friday, we will start on our next set of axioms, which will be the Congruence Axioms. Usual office hours, today and Wednesday after class, and from 2 to 3, tomorrow at 11 and at 1. And no homework for today. I'm planning on sometime between now and class on Wednesday posting a homework 4 for you with a few questions about applying and using the Betweenness axioms. But in the meantime, worry about other things. Any questions or comments before I pass out today's quiz? So I'm going to give you a bit longer for today's quiz. Let's say maybe take about 15 minutes and then potentially more. We'll see how it's going. This quiz has 2 sheets of paper. The actual quiz is front and back of this page. And then the last page is just a list of all the axioms. If you want to rip it off and use it, you can. With that, here you go. Have fun, everybody. If you finish early, draw a picture of Dr. Arn plotting some sort of mission.
So does Dr. Arn in general?
Yes. I mean, I don't know what you're talking about.
Thank you.
Being practiced. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Pass your quizzes forward, please. Alrighty, so what do you call a mathematician who works on a farm? You think?
No, never mind.
Sure?
Well, I heard farm, then I thought protractor, but that doesn't make sense.
That is in fact what I was going for. We call them a protractor type of person. That's a shout out to my sister who works at John Deere. Okay, so I'll get these quizzes hopefully back to you on Wednesday. So last time we were in the middle of proving proposition 3.1, which says if you have 2 points, A not equal to B, then the intersection of rays AB and BA is going to give the line segment AB And then the union of rays AB and BA is going to give the set of all points that happen to lie on the full line AB. Where if you recall, if we say, here's A, here's B, and we kind of want to look at what does it mean to be on, say, one of these two rays. The ray AB is going to be basically this set of points. The set of all points that are either equal to A, equal to B, a point in between A and B, or a point P out here that makes B in the middle of A and P. Ray BA is similar, except it goes in the opposite direction. So ray BA is going to contain A, B, points in between A and B, and points out here that make A in the middle between those points and B. And we claimed that last time that the intersection of these two rays is just going to be the segment AB, and the union is going to basically give all the points on your line. Becca, can you remind me, what does it mean to take the intersection of two sets?
Isn't that just all the points are in both of the sets?
Ah, the points in both of the two sets. And how about the union?
The union is like, you take every point that's in one of the sets and every point that's in the other set and make your sets.
Yeah. So the intersection, you may recall, is going to be the set of all points in both of these two sets, whereas the union is the set of all points that are in either one of these two sets or potentially both. So we're claiming that the intersection is just this line segment, that the points that are in both of these rays consist of points in the line segment, and the union, meaning the points that are either in this ray or that ray or both, is going to give us every point on our line. And last time we were in the middle of proving part A. So for a quick recap, the last time in non-Euclidean geometry, we proved that the intersection of the two rays is a subset of AB, i.e. all points in the intersection of the two rays have to also be points on the line segment AB. And to kind of finish up our proof, what do we still need to show? We know every point that's in the intersection of the two rays is also going to be a point on the line segment. If we want to show that these two sets are exactly the same, Megan, what do we still need to show to finish our proof?
We show that the point in the line segment would be in the intersection.
Yeah, we also need to basically make the same argument in reverse. We need to show that every point in the line segment AB has to also be a point in the intersection of the two rays. So now, in other words, we need to show that the line segment is a subset of the intersection of the two rays. So we must now show that AB is a subset of AB intersect BA. So this symbol right here is the mathematical symbol. I forget if I introduced this last time, that says is a subset of. And basically what this means is we need to show every point in AB, in the segment AB, has to also be a point in the intersection of the two rays. So let's do that. I'm going to start by letting P be an element of the line segment AB. If P is a point in our line segment, what do we know about P? P?
P is between A and B.
Then P is between A and B. Does P have to be between A and B? Okay.
It could also either be equal to A or equal to B.
Yeah. Or we could have that P equals A or P equals B. Because when we talk about a line segment, we usually want to include the endpoints of the line segment, as well as points in the middle. So if we go to our definition of these two rays, length. If P equals A, P equals B, or P is between A and B, is P going to be an element of this set? No. P equals it. Yeah, because this set contains points equal to A, equal to B, and points in between A and B. How about that set?
Same thing.
You sure? I don't see any A star P star B in this set.
Well, A star P star B equals the same thing as A star P star B.
A star P star B equals A star P star B.
B star, you know what I mean. You can flip them.
You can flip them. So meaning if
Betweenness axiom 1.
so by betweenness axiom 1, if P is between A and B, then P also has to be between B and A.
Too many stars in this.
Yeah. So according to the length, we can say that in any of these cases, P is going to be an element of the ray AB by definition, because all three of these possibilities are going to be types of points that the ray AB includes. The ray AB also includes points where B is in the middle, but we don't need to worry about that since P can only be one of these first three cases. And I would say in addition, if A star, P star B, then B star, P star A, by betweenness axiom 1, Elaine, as you pointed out, and thus, in all three cases again, P has to also be an element in the ray BA. And let's see, step. If P is going to be an element, if we know that P is in the ray AB, and if P is also in the ray BA, what do those things combined tell us? Well, we assumed that at the start, but what do we get if we combine these two facts? In other words, what would we like to show P has to be an element of that these two things combined are going to tell us?
P is in the intersection of them?
Yeah, P has to be in the intersection of the two rays. So thus, since P is going to be an element in the ray AB, and P is in the ray BA, we know P has to be in the intersection of the two. And thus, if we combine what we just showed, according to Steph, we now know that AB is a subset of AB intersect BA. And so these two sets are equal. Where here, in order to say that they're equal, we need to not only use that every point in AB is a point in the intersection of the two rays, we are also going to be relying on what we showed last time, that every point in the segment, no, that's not what we showed last time. We also need to use what we showed last time, which is that every point in the intersection of the two rays also has to be an element in the line segment AB. So that if you sort of combine this fact with that fact, that's going to tell us that these two sets are equal. The intersection of the two rays is equal to the set of all the points in the line segment AB. Any questions, comments, or concerns? Dr. Gersel, that feels really obvious. I mean, just look at the picture. Yeah, well, who says that our definitions of betweenness and such have to look anything like this picture? So, again, as with our proofs back in the incidence geometry section, when we prove things that may feel intuitively obvious, we're not only going to be proving them in the cases in the models where we're using our intuitive definition about points, lines, betweenness, etc. We now know, well, at least for part A of this proposition, we now know that that has to hold true no matter what model we're looking at of the betweenness axioms, even if we're looking at a model that's very counterintuitive. I don't want to do, if you all are okay with it, I'm going to skip part B. It's pretty similar. You do a lot of replacing ands with ors. Maybe that can be a homework problem or something. Things to think about. Okay, so one more proposition I'd like to prove using the betweenness axiom. And this one I think is a more fun one than what we just proved. I wanted to go through this proposition to kind of show you how do you show that two sets are equal. You show two sets are equal by showing every element in the first set is an element in the second set and vice versa. It's kind of a common type of mathematical proof. But this one is more spicy. In that this proposition is going to say that every line bounds exactly two half planes every line bounds exactly two half planes, and these half planes have no points in common. What does that mean? So if I were to draw out a line here and say that this line is going to bound exactly two half planes on the board, what do we mean by that? Yes, Jared? Sounds like you.
The one, so still on the board, all the lines on one side and all the lines on the other side.
All the lines on one side and the lines on the other side, or what?
And we have definitions of sides from betweenness axioms. Of that line, did we put points on the line?
Does it have to have points?
No, but we could, like, otherwise it's hard to name the line. We can call it L. Yeah, all the lines on one side is one half plane, and the lines on the other side is another half plane.
I'm not sure what you mean when you say lines on one side.
Oh, no, I'm sorry, points.
Ah, points!
My bad.
That makes more sense to me.
Yeah.
So basically you say the line is going to divide up all of the points into points on one side and points on the other side?
Mm-hmm.
Lucas, what were you going to say?
Pretty much the same thing.
Yeah, I would agree with this. So what this is really saying, and here we're kind of introducing a new term. We haven't actually defined what do we mean by a half plane precisely. What this means is the plane, the set of all points not on L, Because of course you don't have, of course if you have a point on L, then it's not on the same side or opposite side of L as anything else. But the set of all points not on L can be divided into points sharing one of two sides. With no overlap. Let's see if we can prove this result. That we can take all the points not on our line and divide them up into points on the same side of L and points on another side of L. And particularly what we want to show is that we only have two sides. That there's not like three sides of this line. You can't have points that are above the line, below the line, and this direction from the line. Now, we're claiming that lines have two sides to them. Let's see if we can show this. So, a little picture up here, L, that we'll work with. So first of all, we're going to let L be a line. I claim that there has to be a point O on this line. Why do we know this line has to have a point on it? That?
Instance axiom 2.
Instance axiom 2 tells us all lines have to have at least 2 points on it. So I would say that's a good valid line of reasoning. So by instance axiom 2, there exists a point O on L. And I also claim there exists a point A not on L. How do we know that? Nathan?
Instance axiom 3
Instance axiom 3, what does that tell us?
tells us that there exists one point that doesn't lie on any given line between two other points.
And because there's 3 non-collinear points, so any line can't go through all 3 of them, so there has to be at least one line that's not on them?
Yes.
Or one point that's not on the line?
Yes.
I've got one better for you. We're not going to use instance axiom 3. We're going to use proposition 2.3, which says directly every line has a point. Given any line, there exists a point not on the line. And if you recall, we actually talked about proposition 2.3 in class, and it heavily relied on instance axiom 3, on the existence of these 3 non-collinear points. So yeah, if you wanted to, you could cite instance axiom 3, but then it would require a little bit more explanation as to why there's a point not on the line. Whereas proposition 2.3 just says it directly. Given any line, there exists a point not on the line. And one nice benefit of having proved proposition 2.3 from the instance axioms is that one nice benefit of that is that we can use that as a result now without having to go back and rederive that result each time. Which if we just wanted to rely on instance axiom 3 again, we would have to rederive that result. Since we already proved it, we can just use it and not have to worry about justifying it anymore. So finally, I claim there exists a point B such that O is in the middle of A and B. How do we know that? So by some result, we know that there exists a point B such that O is in the middle of B and A. Or between A and B, however you want to write it. What's going to tell us that? Okay?
Is that betweenness axiom 2?
I think betweenness axiom 2 is going to tell us that. Yeah. The fact that part of Betweenness axiom 2 says given any 2 points on a line, there exists a point on the middle, between them on that line. And so if you just take the line going from A to B, or between A and B, there should exist a point, or from A to O, sorry, there should exist a point B that makes O in the middle there. That's a part of Betweenness axiom 2. So we have 3 points. And the existence of all 3 of these points, one on the line, one off the line, and another one on the opposite side of the original of A, a point B. And the fact that all these points exist come from an incidence axiom, a proposition that we proved using the incidence axioms, and a betweenness axiom. So I'm going to claim that A and B are on opposite sides of L. What is that? What did we mean when we say that 2 points are on opposite sides of the line? That?
We said that 2 points are on opposite sides of a line if the line segment between them intersects the line.
Yeah, and so does the line segment between A and B intersect L? Where?
At point O.
Indeed. Yeah, we know that the line segment AB intersects L at the point O by how we constructed B. And so that's then going to tell us that A and B are on, quote, opposite sides of the line L, unquote. Since AB intersects the line L at the point O. So thus, L has at least 2 sides. In other words, what we just showed is that given this line L, there exist points on one side of the line, there's a point up here, A, and there exists a point on opposite sides on another side of L from the point A, namely this point B. So we know that the line L has at least 2 sides to it, the side that A is on and the side that B is on. How can we show, though, that there isn't a third side? Yeah?
Using Betweenness axiom 4, in which it states that if a point is on the opposite side of one line, then it's going to be on the same side as another point that's on the opposite side of one point.
And we need a second to process that.
So if we have point C, and it's on the opposite side of point B, if it's opposite to point B, and A is also opposite to point B, then we know that A and C are on the same side.
So we can't have a third side, and that if we have a point C that's not on the same side as B, then it has to be on the same side as A, and thus it has to be on either the same side as B or the same side as C, or as A. I like it. And you're right, it is a mouthful. It's hard to say all these out loud, which is why I think it's good to kind of try and carefully write this down in words. Yeah, I would agree. Let's erase the board. So yeah, now I could say something like, then given any point C not on L, I think we can say if C is not on the same side as B, meaning if we know that the segment CB intersects the line of L, by definition, if C and B are not on the same side, meaning this segment doesn't not intersect L, then it has to intersect L, and so B and C have to be on opposite sides. It is on opposite sides of L to B. And then Brianna, if we know that C is not on the same side as B, C is on the opposite side of L to B. And can you repeat what your conclusion was from that?
Then C and A have to be on the same side because A is opposite to B as well.
Yeah. So then C is on opposite sides to B, implying since A is also on opposite side to B, opposite has two O's, Dr. Gerson. Sides to L of B, of L to B, that A and C must be on the same side? And what was your justification for that?
Betweenness axiom 4.
Betweenness axiom 4. I like it. The axiom that says if A and B are on the same side and B and C are on the same side, then A and C are on the same side. But more relevant to what we're talking about, if A and B are on opposite sides and B and C are on opposite sides, then A and C have to be on the same side. And here, that's the part of betweenness axiom 4 that we're going to use to say if C is not on the same side as B, so C and B are on opposite sides, since A and B are on opposite sides, by what we said before, betweenness axiom 4 tells us A and C have to be on the same side. And what does that prove now?
That there are only two sides.
That there can't be more than two sides. If C is not on the same side as B, then it has to be on the same side as A. So the side that A, you can't have a side in addition to the side that A and the side that B are on. Thus, L can only have two sides. The side with A and the side with B. And that's what we mean when we say a line is going to divide up all of our points into two separate. Our line is going to divide all the points not on that line into two separate sides. In this case, a top side and a bottom side. But in general, it will always be two sides, no matter what our intuition might tell us about sides. This will be true in any model of the betweenness axioms. Any questions or comments? And with that, we're done with our discussion of the betweenness axioms. Except, spoiler alert, once we get to our next set of axioms, we're still going to be assuming both the instance and the betweenness axioms going forward. So on Wednesday, we'll have our bonus fun day, where we talk about different sizes of infinite sets. And we play a game, you all versus me. And in the meantime, have a good rest of your day. I'll see you all on Wednesday. Nice job today.